Welcome to a deep dive, everybody, and get ready because this one is really going to stretch our imaginations.
Oh, yeah.
We're going to be looking at how the universe might be structured, like
Right.
fundamentally structured.
Like the operating system of reality, right?
Exactly, like the operating system of reality.
Yeah.
And our source material today is kind of fragmented.
Okay.
We have some excerpts from a larger text and an AI's attempt to summarize it.
Oh, interesting. So we're piecing together a puzzle here.
Exactly, but that makes it kind of fun.
Yeah. It adds to the mystery for sure.
Yeah, for sure.
Yeah.
So what I think is really exciting about this is that we're peering into the very cutting edge of theoretical physics.
Yeah, this isn't textbook stuff.
Right.
It's like we're right there on the edge of the unknown.
Yeah, and the big idea that really hooked me was this. What if entropy, that tendency towards disorder,
Right.
is actually a driving force in the universe?
Interesting.
Like a force that creates structure and complexity.
Okay. I like where this is going.
That's what we're going to explore.
All right. So how do we start to even wrap our heads around that? Because most people, when they think of entropy, they think of chaos, randomness.
Right, things falling apart.
Exactly. But the key to this whole idea is something called the entropy scalar.
The entropy scalar.
I mean, it proposes something much more interesting than just, everything dissolving into disorder.
All right, I'm all ears.
It suggests that instead of energy just spreading out evenly, like imagine heat dissipating in a room.
Okay, yeah.
What if energy flows in specific directions,
Interesting.
creating patterns and structures?
Like it's being guided almost.
It's like the difference between a river that just randomly floods a plain versus carving out a canyon over time.
Oh, I see.
The entropy scalar is trying to quantify that directionality.
So it's not just about energy spreading out, it's about how it's channeled or almost like it's being guided, right?
Exactly. And this is where things get really wild because the entropy scalar isn't just a passive observer. It actually has three key functions, at least theoretically.
Oh, wow.
Okay. So first, it tracks how energy dissipates, like a cosmic accountant.
Okay.
Second, it measures the complexity of a system.
So how much information a system contains.
Exactly. And third, and this is the really mind-blowing part, it might be the driving force behind the universe's expansion.
So we've got this entropy scalar that's measuring how energy is flowing. It's somehow connected to how complex things are.
Right.
And it's pushing the universe to expand. How are those even related to each other?
That's the big question.
Yeah.
That's what we're trying to figure out. But the source material hints at this mind-blowing link.
Okay.
What if the structure of the universe itself is constantly changing, and those changes are actually influencing how energy flows and how complexity arises?
I'm trying to keep up.
It's a lot, right?
But, we're talking about the fabric of the universe here, the fundamental laws of physics.
Yeah.
How could something as seemingly stable as those laws be changing? That's what I don't get.
Well, that's where things get even more interesting. The source material points to a constant that we thought was constant.
Okay.
The fine structure constant.
Okay, I've heard of that.
Right. This number dictates the strength of electromagnetism, which is, one of the four fundamental forces
Fundamental forces of the universe.
in the universe. Yeah. But recent research is actually suggesting it might fluctuate
Fluctuate.
in different parts of space-time.
Hold on, so you're saying that electromagnetism could be different depending on where you are in the universe?
It's pretty wild.
That seems like it would just totally change everything.
And that ties back into the entropy scalar, because those fluctuations could be directly tied to those asymmetrical energy flows that we were talking about.
Okay.
Imagine if the fine structure constant, these little ripples,
Yeah.
are actually creating the currents that guide energy and shape the universe.
So like a feedback loop.
Exactly.
The structure changes, it influences how energy flows, which creates complexity, which maybe even led to us.
It's a pretty amazing idea, right?
Yeah.
A universe that's way more dynamic
Yeah.
than we ever thought.
More interconnected.
Yeah, way more interconnected.
It's a lot. But let's get down to, like what we can actually see, right?
Right.
We see stars, we see galaxies, we see planets, we see life.
Yeah.
How do we go from these really abstract ideas to the reality that we see every day?
Okay, so let's get concrete.
Yeah, let's get concrete.
Think about how quantum particles interact. They're constantly changing states, forming and breaking bonds, creating the structures that we observe.
Yeah.
Now imagine these fluctuations in the fine structure, constant,
Yeah.
like little nudges that are influencing those interactions,
Okay.
shaping the outcomes.
So they kind of tilt the playing field a little bit.
Exactly. And over vast stretches of time and space, those tiny little nudges add up,
Okay.
to huge effects.
It's like the butterfly effect, but cosmic, right?
Exactly, yeah.
Okay, I get that, but how do we know any of this is actually happening?
That's the question, right? Like, is there evidence?
Right.
Well, there are some tantalizing hints.
Okay.
When astronomers look at light from very distant quasars, it actually suggests that the fine structure constant might have been different in the early universe.
So we're literally looking back in time
We are.
and seeing different physics.
It's amazing. And there's more. The cosmic microwave background radiation, which is that, afterglow of the Big Bang.
the oldest light we can see.
Exactly. It contains subtle temperature variations.
Okay.
And those variations could actually be fingerprints
Wow.
of those early asymmetric energy distributions we were talking about.
So we're seeing evidence from the very beginning of the universe.
From the beginning, yeah.
Yeah.
It's like seeing the entropy scalar at work from the get-go.
But how does all this connect to the universe we see today?
Well, if the fine structure constant was fluctuating in the early universe,
Yeah.
it could have influenced how matter clumped together,
Oh, okay.
seeding the formation of galaxies and clusters of galaxies.
Oh, I see.
Even the way stars form and are distributed
Okay.
could be influenced by these same principles.
So something as huge and majestic as a galaxy could be a product of these really subtle forces.
It's an incredible idea.
It's kind of humbling and amazing at the same time.
It is. It is.
But what about the really extreme stuff, like black holes?
Oh, yeah. Black
They
holes.
push the limits of physics.
Yeah, they're really the key to unlocking some of these secrets.
Why black holes?
Well, because they are the ultimate examples of energy density
Okay.
and gravitational forces.
Yeah.
If the fine structure constant influences how energy behaves, then black holes, as these colossal concentrations of energy, should be profoundly affected.
Oh, okay.
It may actually be these cosmic laboratories
Wow.
where we can actually see the interplay of these forces on a huge scale.
Okay. Let's take a breath for a second,
Okay.
because my brain is starting to melt a little bit.
Yeah, it's a lot to take in.
So we've been talking about this potential fundamental transformation equation,
Right.
this way of understanding how the universe evolves and changes. And the core of it is this idea that entropy, which we think of as this force of chaos, might actually be a force of creation.
A creative force, yeah.
A force that shapes the universe.
Shaping things rather than destroying things.
Yeah, it's wild.
It is wild.
And the key to understanding this might be the entropy scalar, this measure of how energy flows in a very specific direction, creating complexity.
Structure, yeah.
And then we have the fine structure constant, which might not be so constant.
It might be fluctuating.
These fluctuations could be like these little ripples
Yeah.
that are driving those energy flows.
Shaping the universe from the very beginning.
This is mind-blowing, and I'm sure our listeners want to hear more.
I'm sure they do.
But we're going to have to save it for the next part of our deep dive.
Okay, we'll be back.
We'll be back
With more mind-blowing stuff.
More mind-blowing stuff, yes.
Exactly.
Looking forward to it.
So stay tuned, everybody. Yeah, stay tuned. Welcome back to our deep dive, everyone. We're picking up right where we left off, contemplating this fluctuating fine structure constant.
Yeah, and the entropy scalar. You know, all this talk about cosmic forces shaping galaxies and black holes. It's incredible. But I'm also thinking, what does it mean for us?
For humanity, right?
Yeah, for humanity.
Yeah.
Like, if we could understand these forces
Mm-hmm.
and maybe even control them, what could we do?
Well, that's the question, isn't it? The source material actually touches upon some really mind-boggling possibilities.
Okay, now we're talking. Like, are we talking science fiction level stuff, or is this just pure speculation?
A little bit of both.
Uh-huh.
But even the speculation is rooted in some serious science.
Okay.
Like, let's start with something that's already on the horizon. Quantum technology.
Quantum computers, entanglement. That stuff's already blowing my mind.
Right, it's pushing the boundaries of what we thought was possible.
So how would understanding the entropy scalar and a fluctuating fine structure constant change things?
Well, imagine quantum computers that are not just faster, but fundamentally different.
Oh, wow.
Able to tackle problems that are impossible for even the most advanced computers today.
Give me an example, like what kind of problems?
We could design new materials, understand complex biological systems, even maybe crack the code of consciousness itself.
Whoa, we're talking about a whole new level of understanding. But, okay, let's get a little bit more sci-fi here.
Yeah, let's push the boundaries a bit.
What about manipulating space-time?
Ah, you're thinking wormholes.
Yeah, like is that even remotely possible?
Well, it's definitely in the realm of science fiction at this point.
Okay.
But there are theoretical physicists who believe manipulating the fine structure constant could actually lead to creating stable wormholes.
Stable wormholes.
That would allow us to travel vast distances across the universe.
That would be amazing. But wouldn't messing with space-time be, like, insanely dangerous? Could we create some cosmic catastrophe?
It's a valid concern, and one that any responsible scientist would take very seriously. But that's why understanding these concepts is so crucial.
Right, we need to know what we're doing.
We need to walk before we can run, especially when we're dealing with the fabric of reality.
Exactly. But, okay, even if wormholes are a long way off, there are other applications that are still pretty amazing, right?
Oh, absolutely.
Yeah.
Our sources talked about the idea of cosmic engineering.
Cosmic engineering.
If we could really grasp how energy flows shape the universe, we might be able to influence the formation of stars, planets, even entire galaxies.
We're talking about building planets and stars.
It's a concept with incredible potential, but also enormous responsibility.
Yeah, no kidding.
We could terraform planets, create habitable environments in space, maybe even see new life in the universe.
Now that is a legacy. But let's bring it back down to Earth for a second.
Okay.
What about the more immediate implications? Like, how could this knowledge change our lives in the near future?
Well, even without warping space-time or building new worlds, this knowledge could revolutionize our understanding of energy. Imagine tapping into the fundamental forces of the universe for clean, limitless energy.
Yeah, that would solve a lot of problems. No more fossil fuels, no more energy shortages.
Exactly.
But, okay, we've been kind of dancing around the biggest, most mind-blowing possibility from the source material.
Oh, you mean?
Creating new dimensions.
You want to go with it?
Yeah, I do. The source material says if we can manipulate the fine structure constant in very specific ways, we might create conditions where new dimensions could emerge. Like, is there any scientific basis for that, or are we just in fantasy land now?
It's definitely at the bleeding edge of theoretical physics.
Okay.
The idea is that there might be extra dimensions that are like curled up and hidden within space-time. And by manipulating the fine structure constant, we could unfold them. Make them accessible to us.
Oh my gosh, new dimensions. Like, what would that even be like?
Well, that's the beauty of the unknown, isn't it? We can only speculate.
True.
But imagine the possibilities. Exploring realms beyond our comprehension. Discovering new forms of matter and energy.
It's almost too much to think about.
Right.
But, okay, even if we never get to those extra dimensions, just the possibility that they're out there is amazing.
It is. It makes you realize how much we still don't know about the universe.
And that sense of wonder is what keeps us going.
It fuels scientific progress.
Yeah.
The pursuit of knowledge is just as valuable as the discoveries themselves.
Absolutely. But let's be realistic for a minute.
Yeah.
We've been talking about some really far out stuff.
We have.
Warping space-time, creating new dimensions.
Right.
It's easy to get lost in the what-ifs. But what about the more practical implications? What can we learn from these concepts, even if we never achieve those huge feats?
That's a great question. Even if we never build wormholes or travel to other dimensions, understanding these fundamental forces could revolutionize how we see the universe.
Yeah.
Like, imagine being able to accurately predict the future of the universe, or finally figuring out dark energy and dark matter.
Now, that would be a scientific revolution.
A total paradigm shift.
Yeah.
And it all comes from exploring these seemingly abstract ideas.
Yeah.
The entropy scalar, the fine structure constant.
They might hold the keys to the universe.
They might.
So where do we go from here? What's the next step on this scientific adventure?
Well, we need to keep gathering evidence to test these theories and refine our understanding.
Of course.
More data, more experiments, more observations from telescopes and particle accelerators.
We need more people like you out there thinking big.
It's going to take a global effort, scientists all over the world collaborating.
Sharing ideas, pushing each other further.
And we need to inspire the next generation of scientists to carry on this work.
That's right. We need to get young people excited about science.
We need to cultivate that curiosity and encourage exploration.
And make science accessible to everyone.
Exactly, not just a select few.
Because who knows? The next Einstein might be out there right now, waiting to unlock the secrets of the universe.
And who knows what incredible discoveries are still waiting for us.
The universe is full of surprises.
It really is. And I, for one, can't wait to see what we uncover next.
Me too. But for now, we're going to have to take a little break from our cosmic journey.
We are.
But join us for the final part of our deep dive.
Yes.
We're going to reflect on everything we've learned.
We'll look at the bigger picture.
And explore what it all means.
See you soon.
Stay tuned, everyone. Okay, welcome back to our deep dive. We've been talking about some really, really complex stuff. A fluctuating fine structure, constant entropy scalar, the possibility of harnessing these forces to do incredible things that seem like they're straight out of science fiction.
It's definitely a lot to process.
It really is. You know, at the beginning of this deep dive, we were talking about how our source material was a bit fragmented.
Yeah, excerpts, AI interpretations.
But as we've gone along, I'm actually starting to see a bigger picture emerging.
Me too, yeah. It's like all these seemingly disparate ideas, entropy, the fine structure, constant quantum state transitions are starting to connect.
Yeah, it's not just the individual concepts, but how they all fit together.
Exactly.
So for this last part of our deep dive, I want to focus on what it all means. What's the takeaway message for our listeners?
Yeah, good question. I think one of the biggest things we've learned is that the universe might be way more interconnected and dynamic than we ever thought.
Yeah, like our traditional view of the universe is this big empty space.
Right, yeah.
With objects just scattered randomly.
The things just floating around.
It's starting to fall apart.
Yeah, it's not holding up.
Yeah.
It's like we've been looking at the universe through a really narrow lens, focusing on individual stars and galaxies without seeing the connections between them.
And the entropy scalar, if it really exists, suggests there's a deeper order.
Like a guiding principle shaping everything.
Oh, hidden code, almost.
Yeah, a set of rules.
That's governing how the universe behaves.
Yeah, we're just starting to figure it out.
And if we can crack that code,
imagine what we could do.
It would change everything.
It would be a whole new understanding of the universe, from the tiniest particles to the biggest structures.
Yeah, and I think another really important takeaway.
What's that?
Is that the universe is not static.
Right. It's not fixed. It's not unchanging.
It's evolving, changing, creating new possibilities all the time.
Yeah, and we're part of that process. We're not just sitting back and watching.
We're active participants.
Exactly. Which means we have the potential to influence the future of the universe.
Wow, that's a powerful thought.
It is. And it comes with a big responsibility.
If we have the power to affect the universe, we need to use it wisely.
We can't just do whatever we want without thinking of the consequences.
Absolutely. But we also shouldn't be afraid to explore these possibilities, right?
Right. Curiosity is what drives us.
It's what makes us human. And who knows, maybe in the process of exploring these really wild concepts, we'll find answers to questions we haven't even thought to ask yet.
That's the amazing thing about science. It's an endless journey of discovery.
Yeah. And even if we never actually warp space-time or travel to other dimensions, just the act of thinking about these things will push the boundaries of what we know.
It'll lead to new insights, new technologies, new innovations.
Exactly. So to our listeners out there, I hope this deep dive has gotten you thinking, maybe even challenged some of your beliefs.
I hope it's left you with a sense of wonder about the universe.
And a desire to learn more. Remember, the exploration doesn't end here.
Keep questioning, keep learning. Keep pushing the boundaries.
Because you never know what incredible discoveries are waiting just around the corner. Thanks for joining us on this amazing journey.
Thanks, everyone.